Yes, Albert. I've just talked to Dr. Callis.
Yeah.
He has requested that maybe chairing another meeting, MBA meeting.
Yeah.
So he has requested that probably maybe we'll start.
We start.
He will join us later. I can do the opening. Then he will join us.
No problem. That's perfect for me.
Okay. Please, participants, we apologize for the delay. My name is Christopher Xavier. I work with the Ministry of the Environment under the Water Resources Institute, where I work as a deputy coordinator. Welcome you to the 23rd Water Resources Institute monthly webinar. For those
I think we've lost Francis, or is it just me? Job, can you hear me, or is?
I think we lost him.
Okay, thanks. So yeah, because I was wondering whether is it just me or we've lost him. So maybe I could just share my presentation and then we'll pick it from there. I guess we could start. Okay. Yeah, so I guess we've lost Francis, and I'll just go ahead with my talk, and then maybe once he joins later, we can pick it up from there. So I'm Albert, and I'll be talking about climate impact attribution of changes in hydrological processes in the Nile basin. And in this talk, I'll focus mostly on river flow and sediment loads. And hopefully, we can share experiences at the end of the talk. I'll probably talk for about 20 to 25 minutes. So I always like starting my talk with, this clip art which says, so how did you solve your city's climate crisis? And people responded, we left. And, this could be through internal or external migrations. But I hope at the end of the talk, you'll feel more or less compelled to somewhat stay and try and solve your city's climate crisis. When we talk about the Nile basin, I would presume that most of the people in this talk are familiar with the Nile basin. So I'll just give some quick facts and then we'll proceed. So this is like the second largest basin in Africa, so the Congo Basin, and it has a catchment area of about 3.5 million kilometers squared, shared by 11 countries, and the hydrological processes within the Nile Basin are characterized by high inter-annual variability, just like its climatology. And one thing to note is also that the river flows within this Nile Basin are modified by natural features, such as wetlands and swamps, but also infrastructures, mostly dams and reservoirs. I did quite a quick, news check about climate change in the Nile Basin, and there are several articles that pop up in terms of climate extremes. So floods, to droughts, to challenges in water quality, to wildfires. So the Nile Basin is not new in this sphere of climate impacts, just like most parts of the world. And also, when we go into this international disaster database, looking at the last 24 years, we can see that all countries within the Nile Basin have experienced one or two or a couple of climate extremes. And this database is also not, super comprehensive because the data comes from NGOs and some of it is submitted by the governments. So you can see that all the 11 countries have experienced one or two or a couple of climate extremes. And when we really go, this really highlights that it's just not anywhere any other parts of the world, but we also have it in our own neighborhood. But when we go into climate drivers, what could be driving this these changes in impact events? When we look at the annual temperature change, just from upstream countries to downstream countries, we can see that we have this increase in temperature change, just like many parts of the world. But when we go to the precipitation patterns, there is really no uniform signal across the Nile Basin. So rainfall has increased while it has decreased in some parts of the basin, and we'll see this in the subsequent slides. But, you know, it's just not the climate that is changing within the Nile Basin. We also have human interventions. So we see that there's a growing population and economic shift in the Nile Basin towards more resource-intensive consumption patterns, which means that also the annual freshwater withdrawals has increased approximately 6 times since the 1900s. And this water is extracted mostly for, you know, agriculture, industry, but also domestic water use. So it's just not the climate that is changing, but also the human interventions within the basin are changing. So then how do we can quantify the role of climate change within the basin? So how do we have a separation of climate change from direct human interventions? Because on one hand, you know, we have this changing climate, but then also on the other hand, we have these non-climatic stresses, such as land use change or reservoirs or dams that are leading to a change in the hydrological processes in the basin. And this is where this concept of climate impact attribution comes into play. Now, this, according to the IPCC, there is this, they define detection, so detecting and attributing changes in the Earth system. They define detection as the process of demonstrating that a climate or a system affected by climate has changed in some defined statistical sense, while attribution is really the process of evaluating relative contributions of multiple causal factors to a change or event in a system with an assignment of statistical confidence. Now, this drawing is from the IPCC 2014. I know it's a bit compact, but let's try and break it down. So the Earth system consists of 3 coupled and overlapping systems. So you have the climate system, the human system, and the natural system. Now, the direct drivers of the human system onto the climate system are denoted by this red arrow when you see number 1. And these drivers are like the emission of CO2. But also, some of these drivers have an impact on the natural system. But there are also further influences on each system that do not involve climate drivers, and these are represented by the blue arrows. So, for example, you have an influence of the human system onto the natural system, which is that blue arrow number 3. And an example of this could be pollution of the river catchment. So if you have industries discharging untreated wastewater into a river directly, this has nothing to do with the climate, but rather the human drivers. So the detection and attribution really comes to try and disentangle these different systems and the confounding drivers. Now, Working Group 1 and Working Group 2 of the IPCC have 2 different classical definitions of attribution. So Working Group 1 is basically focuses on attributing changes in the climate system to anthropogenic forcings, while Working Group 2, for it looks at the difference between the observed or the factual state of the system and the counterfactual baseline. Now, the counterfactual baseline is basically defined as a hypothetical system without climate change. So this is where they remove the signal of climate change and you have this hypothetical counterfactual baseline. And the difference between that and the observed state of the system will give you the impact of climate change on the system. But the counterfactual baseline cannot be observed. So then how do we come about this? How do we solve this? So this is where process-based or empirical impact models come in to fill this gap. So the way the models come in is that these models are forced with the observed direct human drivers, such as, these water obstructions and land use changes, but then forced with a counterfactual climate dataset, so without climate change. And this simulation will give you this counterfactual baseline state of the system. And when you get this counterfactual baseline state of the system, minus the factual state of the system, you will have the impact of climate change or the role of climate change on the system of interest. Let me try and explain it further here. So let's say most of you are modelers, you have the river flow, which is like an impact factor here. So you have your simulated and you observed simulations. So it's simulated and observed time series. And you calibrate your model and you have more or less a good performance replication. So then what you do now is you replace your observed climate data in the model with the counterfactual climate data, and then you will have a counterfactual simulation as well. And for example, when we look at this event, this peak event, so we could attribute this magnitude of event to climate change by getting the difference between the counterfactual and factual state of simulation at that event. Or you could also look at a long-term attribution where you get the trends from the two different simulations, so the counterfactual and the observed or factual simulation, and that difference will be the attribution to climate change. So the concept is that, you set up your regional model or whatever catchment model you have, and it could be, just not a hydrological model. It could be an agricultural model. It could be a biodiversity model. It could be a forest model. And then you calibrate and evaluate your model. In our case, we focused on flow and sediment load in the study. Then now you force your calibrated model with your counterfactual climate data, and the difference between the model simulations will give you the role of climate change on your impact factor. So we now apply this concept that I've mentioned here into the Nile basin. So the Nile basin is made up of about 10 large subbasins. And in our attribution study, we focused on 6 stations for river flow and 2 stations for sediment load that are more or less spatially distributed, mainly in the Lake Victoria Basin, the Blue Nile Basin, and the Main Nile Basin. And I will show you why we use this 6 stations. So we used a SWOT plus model. So this is a soil water assessment tool, and it's a semi-distributed, physically based ecohydrological model that relies on the physical characteristics of a catchment, and it's mostly governed by the water balance. So the way it works is that you have a catchment that is divided into sub-catchments that are later divided into HRUs. These are hydrologic response units. So the way the HRU is that you have this elevation, the land use, the soil, and the areas with the same soil, land use, and elevation are categorized into HRUs. And this is the smallest unit of simulation. Then with your climate data, you can be able to simulate your river flow, your water quality constituents, crop yields, to mention but a few. The source code is in Fortran, but it has a graphical user interface, and also you could apply also Python to sort of analyze your results, but it's very user-friendly. But and then like I mentioned earlier on, is that with this attribution, with this impact attribution, that you have to get your physical processes in the observed state of the system more or less realistically represented. So we try for the Nile basin to really capture most of the processes, including reservoirs and dams, crop rotations, agricultural practices, point sources, so that we have this more or less realistic representation of the observed state of the system. And we employ mostly global datasets from the Inter-Sectoral Impact Model Intercomparison project. It provides really open access global datasets that you can use in your modeling practices. And why we use these global datasets is for us to have reproducibility of these results. So in case you want to set up this model again with the same datasets and the same modeling framework, you can be able to reproduce our results. And it's really freely available. So if you want to really go into details of the setup, the calibration, the how we try to optimize the model to simulate soil erosion and sediment yield processes, crop practices, reservoirs, check out these works that we've done with different collaborators along this journey. So for the model evaluation, we focused on 18 stations and sediment load for river flow, 18 stations for river flow and 2 stations for the sediment load. For the sources of the data was mostly from this GRDC dataset. So it's the Global Runoff Data Center, and also the GEMSAT, which is this water quality global database. However, it's good to mention that there's limited soil erosion and sediment load data, not just in Africa, but I would say globally, there's limited observed data. And I will also show you how we incorporated in remote sensing data to sort of close this gap. So for the 18 stations that we calibrated our model with, we selected the stations that performed well, because the concept of attribution is that you have to be able to reproduce your historical processes. So if you want to do a flow attribution, you have to be able to reproduce long-term these flow simulations. So we selected stations that had high-performance statistical indicators and that could reproduce these historical long-term flow simulations. And it's good to also highlight, like, for example, at the Owen Falls Dam, you can see that we captured the seasonality in our simulation, but we didn't get the magnitude correct. And this is because it's controlled. And without this data of releases, it's very difficult to reproduce the exact simulation. And when you look at like Malakal, which is in Sudan, with the Sud swamp, you find that if you can't represent all these swamp and wetland interaction processes, it's very difficult to get the simulations right. So this also highlights that still within our modeling processes, we still have limitations on how much we can represent some physical processes within these models. For the sediment load, so we also had a proof of concept in terms of using electability data to evaluate our temporal and spatial patterns in river sediment load data. And we tested this proof of concepts within the Lake Tana Basin, and we later upscaled it to the African continent. So here we try and use electability data as a proxy for river sediment load to really bridge this gap of sediment load data that we do not have in Africa. But for the attribution, we selected KC and CMU stations because these are the only stations in the Nile Basin where we could get a long time series of sediment load data, observed sediment load data. And we were able to reproduce these patterns using our model, and you selected these for the attribution analysis. So for the attribution, like I mentioned, it's just the difference between our model simulations forced with counterfactual climate data vis-a-vis simulations forced with the factual climate data. And we also did some statistical analysis or using this Mann-Kendall trend test for assessing increasing or decreasing trends, as well as the sense of to estimate the magnitude of the trends and see if actually these trends are significant or not. So the attribution results, when we look at the river flow, we see that for the selected stations in the Nile Basin, we saw this upward trend, and the long-term, the changes in the long-term mean of the annual river flow between the counterfactual and factual flow climate forcing data for the CMU and Mara was 53%, 53 to 11%. And this was really the contribution, the role of climate change as calculated between the difference between the two long-term mean average for the two model simulations. And for the selected stations downstream of the Nile Basin, we could see a predominantly decreasing trend vis-a-vis compared to the upward trend in the upstream of the basin. However, also downstream of the basin, the changes were very they were less than 10% for all of the stations that we selected. And for the sediment load, we see that we mimic the same. When you look at the upstream and downstream, we mimic the same patterns as in the river flows, where we have an increase in the CMU catchment, but a decrease in the KC station within the Blue Nile. So we just see that really sediment load follows the same exact pattern as the river flow. So we try to also analyze the annual precipitation trends to see, because we know that precipitation really is a key driver for river flow and sediment load. So we also look at the precipitation, and we see that actually the river flow and the sediment load follow the same precipitation patterns. When we see in the Victoria Basin, we see an increase both annually and at the 95th percentile. As well, when we see in the Blue Nile, we see a decrease both annually and the 95 percentile. So we see that really this sediment load and river flows follow these precipitation trends as well. So some takeaways from this work was that, for the selected discharges we see, it highlights, a varying nature of climate perturbations, where we see a reasonable evidence of a long-term historical increase in river flows and sediment loads of the headwaters of the White Nile, specifically in the Lake Victoria Basin, while we see a less impact of climate change on river flows and sediment loads in the Blue and the Main Nile Basin, but then also these trends are actually decreasing. However, it's good to note that when you look at 3.5 million kilometers squared of the Nile Basin, and we only selected 6 stations for river flow and 2 stations for sediment load, we have to know that, this brings about uncertainties when we would want to interpret these results to a broader basin context. So, we hope that in the subsequent studies, we can incorporate in more gauging stations to have a comprehensive analysis of the Nile Basin. So when we try to position our attribution study in this global context of climate change, we see that, these attributions provide valuable insights for climate negotiations, or even just in attributing damages due to climate change. For example, this attribution study, could inform when we categorize Uganda as a developing country, we can see that it could inform, onsets of extreme events or even slow onsets of impacts, which then affects the vulnerable developing countries. So you look at the lower category of the lower category here, the blue chain. But when we look at, for example, for developed countries, let's say we had done this attribution in a developed country, then it could be provide these economic and political considerations in those countries, which then influences these countries that contribute money to the funding mechanism later, the payout of developing regions. But of course, this is because you don't have, this key separation of climate change from these direct human interventions as drivers of observed changes in our natural, managed, and human systems. Also, these results can, also provide information on shaping adaptation strategies. For example, we've seen that the different parts of the Nile Basin are undergoing different or opposite changes in terms of trends in river flows and sediment loads. And this provides a better understanding of the drivers of the observed changes in the basin. And there's also this recent concept of climate risk insurance, which is mostly in developed regions. But the idea is that because these developed regions provide an insurance subsidy to the population, so if you can be able to attribute the losses that occur due to climate impacts, then the scale of the problem is that you make governments start to appreciate the increased costs as they can expect when these natural disasters happen on the scale of this risk spectrum. So if you would like to dig more into the work, it's publicly published and available. You can check it out there. And like I mentioned, there's also Joe Bekolo is also among the participants here, and he can also chip in if he wants to add in more context on this work. And also we also sort of like briefly contributed to this work that did an event attribution on Lake Victoria here that explained the role of anthropogenic climate change in the 2020 record breaking of Lake Victoria levels, and found that climate change, anthropogenic climate change has increased this probability by 1.8. So you can also check that study out. I think it's pretty cool and relevant in this context. Otherwise, thank you for listening, and I hope we can have a great discussion. Thanks.
You're welcome.
So I think I'll stop sharing and then look at some of the chat questions. Or right? I think that's better. Okay. Besides data, there's a question by Flavia. Besides data gaps, why was the climate signal unstable at Owen Falls Dam? Nice data points. Why was the climate change signal unstable at Owen Falls Dam? Okay, so in our study, we did not do the attribution at the Owen Falls Dam because like I mentioned, we could get the seasonality right in simulating the outflow at Owen Falls Dam, but we could not get the magnitude correct. So, and the challenge with attribution is that you should be able to reproduce your historical runs more or less close to the observations. So we ignored that because we could not be able to reproduce the magnitude at the Owen Falls Dam in our modeling study. And this was mainly because without data, there's literally no country that provides reservoir data in terms of releases and controls at the dam outlets. So you have to try and reproduce that. And in most cases, it's difficult to get without this data in terms of releases, at least globally freely available data. That was the hugest challenge that we could get, that we got at reproducing the outflows that the Owen Falls Dam. If it's not clear, just chip in and talk, please. And I see a question by Amon, who is like, given the study, can we attribute the recent recurrent floods in Uganda and Kenya to climate change or human influence? Yeah, I think it's very easy for us to, if you've not done a study, like you can't conclusively say. It's very easy for even the policymakers or politicians to come and say, we attribute these floods, it's because of climate change, it's because, we're increasing our emissions and what. But I think you really need to do an event attribution or a trend attribution study to be able to attribute that. Like what we did here was we attributed long-term changes in river flows. But if I was to look at these current floods that are occurring, the best thing would be to do an event attribution study and see if we can quantitatively attribute this to climate change. And also the things that we have to also acknowledge the uncertainties within our attribution studies. So the concept would be to also present the attribution study, but also acknowledge the uncertainties within these attribution statements that we make to avoid also misattribution. Yeah, I hope I answered it somewhere, somehow. If you have any questions, please just speak out. Or if you want to say something or add on or share anything, please feel free.
Dr. Mpasi, maybe I can ask my question direct.
Yes, sure. Please.
There was a slide where I saw flows were showing 58%, I think, in upstream countries, and then in the downstream, most of them were negative.
Yes.
So I'm a bit confused because when this water is coming from upstream, I would expect it to end up downstream, but we do not see that impact downstream. Maybe I did get that clearly, or you can help me understand it more. And what could be the reasons? Is it about the evaporation or?
That's a very good question. And it's more or less the hydrology of the Nile basin. So you have to know that this water comes from upstream, but about 50 to 60% of it is lost in the Sud Swamp in Sudan. So we lose about 50 to 60% of the flows that come all the way from the White Nile within the Sud Swamp. And when we reach Khartoum, where we have the Blue Nile and the White Nile connecting, the contribution from the White Nile is only about 15%, 10 to 15%. Most of the contribution comes from the Blue Nile, so from Ethiopia. So we see that whatever happens mostly really upstream, so in the Lake Victoria Basin, by the time it reaches just at the connection of Khartoum of the White Nile and the Blue Nile, where they connect into the main Nile, we've lost a lot of water compared to what is coming from the Blue Nile. So most of the flows downstream of the Nile actually influence a lot from the Blue Nile. The advantage is that the White Nile is very more or less consistent, so it contributes most of the flows to the White Nile during also the dry periods. But in terms of magnitude of flows, the influence comes mostly from the Blue Nile and not really from the White Nile. So you can see that's why you can have that. You can see a process whereby you can have different perturbations upstream, but then downstream, there's also a different perturbation of climate, or even just river flow obstructions or river flows. I hope it's somewhat clear.
Dr.
Yes,
Albert, before you leave that question,
Yes.
it's like you've answered it, mainly bending it towards the natural factors like seasonality and the hydrology that is driving those changes in the basin. But there are also human drivers like the dams, which are being regulated by man. How do you separate those two if you're mentioning that it's mainly that? Because, for example, at the Owen Falls Dam, there were recent floods like in 2020 and 2021. We had in the newspapers that they had just opened the dams to relieve them. So how do you draw a line on that?
Yeah. Now, attribution comes in two ways, Flavia. You have an event attribution, so a flood is an event. A drought is an event. So those are, you can do an event attribution. Then you have also a long-term trend attribution. What we did in our study was a long-term trend attribution. But also the study that I presented more or less in the last slide was an event attribution that tries to see this, can we attribute this event, a flood or a drought, to climate change? So I will answer your question. I'll first talk about attribution, then later talk about the human drivers that are happening. So if you want to do an event attribution, for example, to see if this flood has been caused by climate change, you have to run simulations with pre-industrial climate forcing. So you have a simulation with pre-industrial climate forcing. So this is a simulation with no climate change. So you fix your radiative forcing to pre-industrial levels. And then you run a simulation as well with climate change. And then you run a simulation with only natural climate variability. And in that way, you can see how a simulation with only natural climate variability vis-a-vis pre-industrial level and vis-a-vis climate change changes, and see how you can quantify your events. For the long-term trend, you look at the long-term, you see, is it increasing or decreasing? You look at the long-term shift, and then you run with your counterfactual climate simulation and see if you can have a difference between this observed long-term trend with your counterfactual simulation. Now, the impact of human drivers is what I mentioned earlier on in the presentation, that with attribution, if you're to do your attribution with a modeling study, you have to ensure that you represent these human drivers. Otherwise, you can easily do a misattribution whereby you assign it to climate change, but you have drivers that are not represented in your models. So that is why, for example, in our model that we set up for the Nile Basin, we were able to try and represent all these reservoirs, the Senna Dam, the Rosary Dam, the Swan Dam, because at the end of the day, these also influence our river flows. So then now, if you have a model that captures more or less all these physical processes, then you force your model with only the observed factual climate and the counterfactual climate, meaning that the only thing that is changing within your modeling process is the climate, but these human drivers are consistent. So then you can quantitatively be able to calculate this role of climate change. I hope that somewhat makes sense. So, for example, like when we go to the downstream where we have really a small impact, we can, from our study, we can quantitatively say that impact, the small impact we have, or the decreasing impact we had, the change, is climate change. But if we were then now to quantitatively be able to add in the role of human drivers to give it a quantitative number, we would then have to run our model simulations with and without human drivers. Then in a way, we can also give the contribution, so the quantitative contribution of human drivers to the changes in river flows and sediment flows. I hope I've not lost flood. Or...
Thank you, Albert. It's clearer now.
And Joe, please feel free to chip in it because you are also part of this work.
Sure.
If you wanna chip in on any part, feel free.
Hello?
Yeah, Pamela, hi.
I had posted a question in the chat. I was inquiring that given the fact that the biggest contribution of the water levels of Lake Victoria is rainfall that falls directly over the lake. And if you investigate the climate signal on that rainfall, is it a very good assumption to say that the flooding of the lake shores of Lake Victoria's one of the major drivers really is climate change resulting from maybe, I don't know if you've studied it, but the results of the climate signal of rainfall directly over the lake?
Yeah, so the last I'm going to share the link of the work that was done. We looked at the 2020 flood on Lake Victoria and tried to see the role of climate change, anthropogenic climate change. So meaning that we really look at not just natural climate variability, but really the contribution of anthropogenic climate change. And we saw that it increased the possibility of that flood happening by 1.8. So meaning that climate change had a role, and also without, remember the levels rose by 1.2 meters, but we know that without climate change, they would have fallen by 0.7 centimeters. So there is a contribution of climate change, but you cannot also throw away the contribution of people settling in there and also the socioeconomic activities that happen along the lake shores. So you also cannot ignore that fact. But then also this attribution study, we also acknowledge that we had a huge ensemble of uncertainty within our attribution study. So still, we acknowledge the role of climate change, but we also know that we had a huge level of uncertainty. And we also acknowledge that we don't ignore the socioeconomic factors that happen along the lake shores. People settling close to the lake shores, of course, then if you have a flood, then you have more loss and damage.
Yeah, I'd also like to add.
Yeah, Joe, please chip in as well.
Yeah, so I'd like to add on the discussion about the recent floods in Uganda. Yes, we do believe climate change contributed, but it's not just that, but it's a combination of natural variability factors and climate change, which exacerbated it. In particular, the recent El Nino and recent warming within the Indian Ocean are primary drivers. We recently did a study on floods in sub-Saharan Africa, and I'm going to share a link to this on the chat if you're interested in looking at this in more detail to understand how natural climate variability. So if you look at the last, I think, 3-4 years, we've experienced an unprecedented warming within the ocean basins. And particularly for these last 3-4 years where we've had unprecedented flooding in East Africa, we see that there's a strong correlation between this warming and the floods that we observe. So it's not just the natural factors, but climate change that also adds to this. I hope that clarifies on that.
Yeah,
I've shared a link in the chat.
Yeah, thanks, Joe. Thanks, Joe. Yeah, and I think it's what we've been saying as well. It's just not. It's very easy to come and say climate change, but there's also natural climate variability. That's natural factors of climate that we also have to factor in, and those are also very, very predominant within the East African region. It's good to quantify the role of anthropogenic climate change, but then also acknowledge that we have this natural climate variability or natural climate factors that also play a role in our changing climate. So when we say climate change, we encompass both anthropogenic and natural climate drivers. I see a question about I'm saying is the model applicable at basin, micro basin level. Yeah. It's really I think the model was predominantly SWOT plus model. This was predominantly developed for catchment and subcatchment applications, but we are in our work we've upscaled it from subcatchment to. We first did it upscale it from a subcatchment to the Nile basin model. We've now also done it on the Africa scale and currently also on the global scale. So we've gone from local to really global application of this model. So at the moment, there's also a global model of SWOT plus. If you're interested in working at any catchment in the world, you can extract that subcatchment or catchment from the global model and work with it as well. It should be freely available soon online as well. I can share some links.
Albert, I have a question.
Yes, please.
This climate model that you're using for ISMIP,
Yes.
Is it one climate model? But do you think the results might have been different if we had worked with a different climate model, for example, from the UK, or I don't know what you can say about that.
Yes, so this work that we did was actually the first study that worked with counterfactual baseline data. So when we did this study, we started this study in end of 2021. That is when we had the first counterfactual climate data from this ISMIP. ISMIP is this Inter-Sectoral impact model, the comparison project for some of you that are not familiar with it. And at this time, we only had one climate model, which was this G3W3. But over the years, by the time this study came out, actually 3 other models had also produced this counterfactual climate data. So currently, you can actually have an ensemble of different climate models and make your study more robust compared to when we started the study, when we only had one counterfactual climate model data. So at the moment, there we have about 5 models. Then you can run this and have an ensemble and have more levels of confidence in your analysis. Yeah, we tried to do this attribution study using working group 1 definition, where we look at pre-industrial and then natural climate variability, as well as greenhouse anthropogenic climate variability. But we could not really get a signal within the Nile basin. And the signal, and this was mostly because, with this pre-industrial, they have a coarse resolution. So applying it on the Nile basin, they consider it very small in terms of using this data. So it's really very easy to use this data if you're working at a much, maybe a continental scale level. That was a challenge we had there. But at the moment, yeah, you can have, there are more models, Job, and you can have this ensemble of models and have more confidence in your results.
Doctor, I don't know if we still have some more time, but I have another question.
Yeah, sure, please.
The sediment, we are focusing much more on the water, but what is the significance of the sediment loading and these studies on sediment in relation to what we are trying to look at?
Okay, yeah, it's a very good question, and I will approach it from there is this quote that says that quality matters for scarcity, which means that you could have enough water, you could have a lot of water, but if the water is polluted, then it's really not available, right? So that is why we also went beyond just looking at river flows, but also looking at sediments. So river sediments also have they cause pollution in our water bodies. Not only that, also sedimentation in our reservoirs. So that would be the implication. And we have to remember that nutrients like total phosphorus are easily carried by river sediments. So they can also give you an indication of how much or your nutrients are also ending up in the river system. But I would like to let you know that it's very, very challenging to model water quality, things like river sediments, because of the data gap that we have. You have to know that when we look at global measurements of water quality, if Africa has like 0.2% of the measurements. So we only have mostly measurements in South Africa. So it's really, really challenging to model water quality. And that is why we also incorporate in remote sensing, because with remote sensing, you have data sets like, stability data, you have trophic state, you have chlorophyll air data, and you can create proxies of the different water quality variables, such as sediments or total phosphorus or total nitrogen. But I think it's really, water quality is a huge data gap that, yeah, in one way or the other, we're trying to close. And there was a paper that I posted that we did for the whole of Africa, where we looked at total nitrogen and total phosphorus. And we provide actually a data set for Africa from 1951 until 2019 of river flow, river sediment loading, total nitrogen, total phosphorus. And we also try and look at it in the SDG framework of measuring this progress towards SDG 6. So you can also dig into it and see how we have these implications.
Okay, thank you very much. Maybe in addition, it also has an impact because sediment transport creates habitats for different biodiversity, aquatic biodiversity. So maybe it could be a point of interest as well in line to sedimentation.
Yeah, true. I think all nutrients are somewhat important to aquatic ecosystems, but they are important to a certain threshold. So that is why you have these thresholds of where you have critical change from, for example, less eutrophic to eutrophic systems, or because even sediments themselves are super important for aquatic biodiversity, but up to a certain threshold. Then if they exceed the thresholds, then you have this harboring of nutrients within the river systems or the lake systems, whereby if you have, for example, a flood event, you can have resuspension of these nutrients. So yeah, all these nutrients super important, but up to a certain critical threshold. I don't know if it's still.
Yes, Albert, I have another question
Yes, Joe.
about this kind of study.
Yeah.
One of the challenges we have with climate modeling is hydrological model uncertainty. So for instance, you may want to carry out a climate change impact study, and you run the study with one hydrological model. And once you do that with another hydrological model, you find that sometimes you do have differing results. So I was wondering, does that sort of problem happen with this sort of studies? And is it something that could be looked into?
Yeah, thanks for your question. Yeah, it's a pretty interesting cool study and a good question, because that is why we talk about, when we go into the modeling practices, we're trying to advocate for open source and making these models available, this data available, so that we can also do this model intercomparison studies. So if you set up your model with a different interface, let's say SWIM or an empirical model, and you make it available, for people to explore with your data sets, then it's very easy to also carry out this intercomparison studies and see how different models would ideally perform or not. But I would like to say that for the historical period, if you capture most of these physical processes right in your model, and you can be able to reproduce your historical trends or observations, then I would expect that the model is more or less, because you're evaluating your model based on the reproduction of these historical trends. The challenge with where the models become mostly different is when we do the projection, because then really now the model structure comes into play, and then you find that the models are actually projecting different trends or directions in the future because of the different model structures, even regardless of whether they're using the same weather data or input data. Then the model structure comes into play. But for the historical trend attribution, I think if the model can be able to reproduce this historical trend, then the models are more or less similar. But the problem now comes when we do this future projection. That's where the models could project different directions. And yeah, it's always this climate change, the advocate for using an ensemble of models so that, you can have more robust more confidence in your results if you can get different ensemble models and maybe take the median or mean, as opposed to using only one, hydrological model or climate model or water quality model in your analysis.
Thank you. Yeah, I think that is the best approach there.
Yeah, I would advocate for it. It's just, I think it's also more, availability at these models, freely available for people to actually access and use and build on. Or do they, do you just set up this model, do it for your case study, and then just throw away this, this model setup and data results? So it's also more like, how can we become more transparent and open with our models and results so that other people can build on it or reuse them for their own studies? Somebody says that posting the presentation. I'm going to try and post it. I can post it in the chat. I don't know if there are more questions or if we can wrap it up. Yeah, so I posted the presentation in the chat in case you're interested in exploring some of those things in there. I'm not sure if Francis is around, and maybe we can try and wrap up if there are no further questions. Francis, are you online?
Yes, Doctor.
Yeah, I don't know if maybe, I guess someone come to a wrap up.
Okay, I thought Dr. Karis would have connected by now, but since he hasn't connected, probably I could close.
Yeah, I guess we can close, and then maybe yeah, we can also plan more, because we also upskill this work to the African continent. So maybe we can also talk later and see if we can also have another session where we also talk beyond the Nile basin, but rather on the African context.
Okay, yeah. Okay, I agree with you. I want to take this opportunity to thank Dr. Albert Wassa for this presentation. I was listening in, the discussion was very, very, very interesting. And we are looking forward to look at the recommendations and outcomes from this webinar. And as the Water Resources Institute and the Ministry of Land Environment will follow up on all the discussions. Once again, I want to thank the participants for sparing the time to attend this webinar, this 23rd webinar of the Water Resources Institute. I want to encourage everyone who could be interested in sharing information, whether it is practice, policy, and research, what they are doing. The platform is open. You just contact the Water Resources Institute. We will be engaging you and taking you through what is necessary, and we'll have an opportunity for you to present and also share with the different stakeholders. Thank you very much, Dr. Albert, once again. I want to close this webinar. Have a nice day.
Thanks, Francis, and thanks everybody for attending. Yeah, see you around.